Good morning, everybody. My name is Ramanujam, and I work at this institute. It's my pleasure to introduce the next speaker, Dr. Balaji Sampath, who is about as different from what you would expect in this gathering. Okay, so I always start, when I talk on math education, I start with saying that, look, I'm not a mathematician and I'm not a math school teacher, and what am I doing here? And Balaji is even more of a radical than me. And so he's a very well-known face to a lot of people who watch Sun TV, because for the last 20 years he has been doing immense work in science popularization. He's written several books, which I would recommend, and he has taught physics at senior secondary level for quite some time now. He did his PhD in electrical engineering from University of Maryland, and about 20 years ago, 96, it was 96, not about 20 years ago, he started a group called Aid India, which has been flourishing, which has been doing enormous amount of work in rural education in Tamil Nadu. And as part of that, he has interacted extensively with teachers, looking at learning problems of children. And when I say he, it's not he, there's a whole group of people involved who have built up a whole body of work on how children have learning difficulties. My interaction with him has been in this regard as well. But especially at the level of senior secondary, mathematics and science, and how students have problems with these, how to address them, Balaji has been doing a lot. Recently, he has been with Aha Guru. Aha Guru is a commercial enterprise, but there's also Aha Guru Foundation. He's associated with the Aha Guru Foundation, and they're looking at using this mobile phone as a medium, using apps to get kids interested in science and mathematics education. And they've got learning modules that you can go through over a sequence and learn. And in particular, there are also apps that send you problems which you solve quickly and try to respond and so on. Okay, so Balaji is very active in these. He's very good at understanding the minds of students, their learning difficulties, and discuss these, and try to find innovative technological solutions as well. And he's going to tell us a little bit about how this technology can be actually used for doing interesting science and mathematics. I welcome Balaji Sampath.
It's a great pleasure. Thank you, Dr. Ramanujam, for inviting me for this session, and it's wonderful to meet all of you, see you here. இங்க எத்தனை பேருக்கு வந்து தமிழ் ஈஸியா இருக்கும்? I mean, I'll mix and talk. Is anybody not okay with Tamil? A couple of you. Okay. I'll mostly speak in English then. Okay. So I'll speak a little bit in Tamil, and mostly I'll try and stick to English. So basically, first question I have, I'm assuming most of you are teaching 11th and 12th standards. Is somebody also teaching 9th and 10th? 8th, 9th, 10th, yeah. So one big jump in mathematics curriculum, I'm sure all of us have been facing this problem, particularly after the CCE at some level, is that kids are now in the 9th, 10th, 8th, 9th, 10th, they're used to saying one term, portions are over. So I have learned, it's like saying addition done. So no more addition for the next term. Next term I have fractions, I may have multiplication, but no addition. So similar, I mean, obviously that makes no sense as we progress, but students come with that issue. The second problem is that over the years, I think partly because maybe a lot of different technologies have come into children's lives across. People are used to internet, they're used to mobile phones, they're used to TV. So attention spans have really shrunk. How many of you feel that? Yeah. So basically but the problem is as we move into higher grades, there is a requirement that children now take one problem which used to take like 1 minute earlier. Now you need problems they need to spend at least 15 minutes, 20 minutes, 30 minutes on just one idea. After 2 minutes, they are off. They don't want to think about it anymore. So do you face this in class? Many of you do, right? So the question then we've been trying to look at is how do we get children to keep their attention? Or rather, slightly turned around, there are times when children are very highly attentive. So for example, when they are watching something that they are finding very interesting or when they are playing a video game, they will not see anything else going on around them. Mathematics in vanda nadula vande konjam paadi 2 minutes ku appuram bore adichirudhu. And a video game ku that attention remains active for a very long time. So one question was, and that's something that we are still working a lot on, is how do you make children, I think the serious problem, particularly as they go into higher classes, is that there is an attention issue and you can't grasp, you take this. Just to understand what is being said, forget solving the problem or coming up with the idea, to understand this requires an attention span of at least half an hour continuously, minimum. 1 hour, 2 hours, maybe even more. But sometimes we don't have that kind of attention nowadays. And so children's attention spans are even smaller. So that was one question. How do we grab their attention, keep them focused? Because there are tough problems. I'm not saying we can make every problem into a 2 minute, 1 minute problem. But then can we get it to a point, are there specific instances when a child is very, very attentive? We found, for example, a few answers. Like you give them a video, like some of these experiments I've been trying out with different children for a while. You do a class lecture. There are some kids who are attentive, some kids who are not. Suddenly there is a discussion going on between you and maybe 2-3 students. They are thinking very deeply. The rest of the class is switched off. But these 3-4 students are having a very detailed thinking discussion with you. Can we replicate this at a time which is convenient for the others? What makes these children attentive, whereas why is that the other kids are not attentive? Often it is a question about answering or trying to find an answer to a question that's bothering them. The most attentive, you might have also seen this in class, is after you conduct a test and you correct it and return back the papers. And then there are kids who are basically trying to argue why their answer is correct. They will spend half an hour arguing with you. You may get bored with it, but no, how many of you have felt this? After you return an answer paper, they come and fight about why their answer was correct. Okay, that seems to be a point where they are very interested in learning more. It's of course learning to basically prove that they are right, but it's still learning. Because for example, that kind of learning moments can be increased. For example, one thing we realized is if you want to give them a long answer to a question, give them a puzzle kind of a question which they will make a mistake. But they think they are right. And then they come back to you, you have to argue with them why they are not correct. That can be also done sometimes with a video. For example, there is a friend of mine, Professor Rajesh Saragopan, who does a lot of these. I'll use one of the examples that he came up with, that he has been trying out with students. Maybe can I use the board? So, I'll just erase this part. So let us say all kids have learnt a lot of theorems on circles. For example, one of the theorems on circles generally would be that if I have a circle and you take a chord here, the angle subtended by this chord at the center if I call this angle, let us say 30 degrees, this angle is probably, I mean, you know that it has to be 60 degrees, right? So the question was, if I have a situation like this is a circle. Sorry, so let me first draw the circle. So this basic idea was that the angle subtended at the center is twice the angle on the circumference. So the question is, if I took this and let us say that this was 30 degrees and we took this is also going to be 30 degrees. Angles in the same segment. Now if I took a point here and I find that this angle is 60 degrees, let us call that point C. What can you say about C? C is the? So are we sure? We know that if C is the center, angle subtended at the center is double the angle subtended anywhere on the circumference. The question is, this is really to do with the idea of IFF, if and only if. Now, it's a nice word to say, and people know that we must generally put it at the end of the, or in the middle of a sentence, so that we'll get marks for it also. But the question really is, the reverse, is that true? If this angle is 60, does it mean that this must be the center? Are there other points? Might be. In fact, must be. Okay, let us, no, but we know another theorem in circles. For example, if I tell you that this angle is 30 degrees, I'm just using 30 as an example. Okay, where and all can this point be? On a circle. Okay, not the full circle. This part of the circle, because that side is going to basically be not 30, right? So every point here it's going to be 30. How many points like that can we think of where this angle will be 60? We can actually draw an entire circle like that, and this part of the circle, not this half, but that part of the circle, all those places the angle will be 60. In fact, interesting point is we can use this, you can give this as a question. They come back and argue, no, it must be center. Then we can have a discussion about this idea that this is 30, a whole set of points becomes 30. Okay, we can call it the locus of all the points, if they are already introduced to the idea of locus, or we can say that it is a set of points where it is 30 degrees, right? So there are a whole range of points where it is 60. So this, for example, when they make a mistake like this, that becomes a good chance to introduce that converse may not be true. Angle at the center is 60, yes, but wherever you have 60 doesn't necessarily mean that it has to be the center. There are so many points. Sometimes construction arguments help. Things like this, one thing that we found is every time a child actually makes an attempt at a question and actually gets it wrong, or thinks I've got it right but has made a mistake, and we can actually create questions of that kind, then the child is very interested immediately for the next maybe several minutes, very interested in learning a lot more. Learning to prove why I was right, but also they don't have too much ego. Many times they are willing to also say, okay, tell me why I was wrong, so the next time I won't be wrong. So I feel that, and that's true partly for all of us also, which is why we many times like challenges. So if you get challenged, suddenly adrenaline goes up, something happens to our brains, and so we start to focus more to learn a little bit more. And can we make mathematics a sequence of such experiences is a question that we have also been trying to look at. And often the problem is that if a child solves this at home, 2 days later if you try to give an answer to that question, by that time they've already lost interest. So many times, in fact, one of the studies done by a couple of people kind of showed that immediately after a child answers a question, if you give them a solution, they are very interested in learning a bit more. particularly if they made a mistake. If they've got it right, they most probably are not interested in looking at the solution. But if you can set so you set a sequence of questions, some of which are correct, then some of which that are wrong. So that way, the idea is that they will start to think in those terms. In fact, in 11th and 12th, we introduced complex numbers. Once maybe a question like this is done in the 11th, one of the possibilities is to link this to complex numbers, to realize that all these points actually have the same angle, 30 degrees. And one way is, suppose I call this a complex number, let's call this Z1. Let's call that Z and let's call this Z2. Now, how do I know what is this angle? With complex numbers, how do I know what is the angle? We know we teach a little bit of Argand diagram in polar form. Okay, so how do you know the angle between two lines in complex number terms? So you can look at, suppose I do either Z minus Z1 by Z minus Z2. Okay, so this is going to give us a complex number. Like actually a very simple example would be, if I take something like this, let's call that Z and let's call this Z1. What is Z minus Z1? You can think of it as an arrow from Z1 to Z. In vectors, we would do this. Because if I call this the origin, this would be the vector Z1 and that would be the vector Z. And so that would be Z minus Z1. The argument of Z minus Z1 would be this angle. Okay, I'm going to now mention a few things, some of it which will not be completely correct. We'll have to correct for it a little later. But the basic idea is that this gives you some angle theta. If I had a Z here, let me call this Z and let me call that Z1. So then I have Z1 minus Z, easier to see. Okay, what would this be? This is Z2. Z2 minus Z will give me this angle if I took the argument. And if I divide Z1 minus Z by Z2 minus Z, what would be the argument of that? It will be this angle between them. So if I wanted to fix these 2 points and keep this angle constant, that means effectively you are saying argument of this must be constant. Okay. Now what is it? What is the locus? These are questions, for example, that come up in the 11th standard book. Of course, the way we would calculate this is to say, let us assume x plus iy, substitute, divide, figure that out. Okay, it's a long process. But if they already know that the locus of all these points when the angle is constant is a circle, or part of a circle, this one is also the same. Because this angle, let's say this angle was fixed at pi by 6. Pi by 6 is 30 degrees. So this is going to be a circle that's going to pass through Z1 and Z2. I'm not saying that they have to necessarily learn to do the problem this way, but if they are able to make that connection, many times that becomes useful. Suddenly they say, oh, okay, complex numbers, vectors, coordinate geometry, they're all actually the same thing, and they seem to be related to geometry which they already know. So one is, of course, moments when kids get excited about learning a lot more. How do we capture it? So for example, we have now an app where students get questions every day. And many students find that 10-15 minutes is what they're able to spend. That's what they think. Actually, they don't even spend that many times. They spend only 5 minutes. They start with the idea that you'll solve this problem. But if they don't solve, then they're willing to see for 15 minutes a video to see why they couldn't solve. Because that is the time where they are willing to say, okay, this I didn't get, but I thought I already got it. That was correct. Why are these guys saying it's not correct? Let me see the solution. Okay. Some people actually don't even see the solution. They argue with me. They send a message back saying, no, I did it like this. Why is that wrong? Which is actually very good mathematics, because what they have to do in see, the whole point in mathematics is, of course, one side learning a whole bunch of new things. But equivalent is to say, what I already know, If it is wrong, why is it wrong? If it is correct, why is it correct? So to keep thinking about that is actually, I would say, even more important than learning new stuff. So let me take another example. Okay, so this is, let us start with something that was done a little earlier with limits and so on. One general problem I have at least been finding, and maybe I would like to also hear from you. This is regarding many students, at least in the 11th and 12th, particularly when they come into the 11th. Till the 10th, they have been doing very well at school. Suddenly in the 11th, you find that they are no longer able to do well. Or they suddenly start feeling, I don't like maths. And in the science group, how many of you find children doing this? Almost. How is it that they were very good till the 10th? They thought they were very good till the 10th, and suddenly in the 11th, they are no longer good. Curriculum is very different. But mathematical thinking is mathematical thinking. No? They don't find, okay. And how many of you have found, how many of you have taught 8th standard math? Okay. Are there students in 8th standard you've thought that they were, or they thought that they were very good in 5th standard? They're very good mathematically in 6th standard. In 8th standard, they have suddenly lost interest in math. Have you seen this? Why does that happen? How is it that kids who think that they are very good at 5th standard level, 7th, 6th standard level, suddenly find that 8th standard they are no longer very good? Okay, so can you please come up, sir? You can come this way, no problem. Anyway, yeah, come. I would like you to just come here and jump over this. Jump over this. Just jump over, yeah. Okay. So now what I'm going to do is maybe place, I don't think I can place 2 of these, but maybe if I was able to bring this, let's take this chair. Suppose I now ask you, why don't you jump over that? Why is that difficult? That you are able to jump over that, no? But you actually, you did, no, but the point was, if I had asked you to jump from the bottom up here straight away, you would have found it difficult. But how did he manage to climb up? He basically going through steps. Now, jumping up a small step is reasonably straightforward. Okay, but when we ask somebody to jump this in one step, it's a big problem. But why should we ask people to jump this much at one go? He has climbed more than he's climbed the chair. You can take this chair and place it here. That is smaller than the steps that he's actually climbed up. What matters is not how high he can jump, but what matters is at what level is he right now. Maybe this is the level of mathematics that we expect. If we can create smaller steps for children to go up, they'll usually be able to make that jump step by step, right? So the question then in mathematics, thank you, sir. Question then in mathematics teaching is not that the syllabus is very high. Yes, we do need to get there. But the point is, we'll need to create steps to get there. And one big difference I find between primary mathematics, why kids found it very easy, or even like 6th, 7th at some level, and then 11th definitely, and even at some level, even when they come to 9th, 10th, they start suddenly finding it difficult, is that we were doing a lot of concrete things in the beginning. So addition was done with many examples. Multiplication was done with many examples. And now we expect to write a formula or a statement, and we expect them to be able to go from here and figure out all the examples on their own. But they are not used to doing it. I mean, at some point, getting them to do that will basically make a big difference. So can we create many smaller steps to help them grow forward? And concrete examples. I mean, they're still in some sense children. Yes, we do need them to do limits. Okay, but they're still figuring out a little bit about, see, the point is using, like I'll give you an example in physics, since he was asking me a little about physics. You know about this formula for accelerated motion. Okay, so one is to write V equals U plus AT. You can always substitute for V, U and A and so on and find whatever you want to. But what I, for example, found was it makes a huge difference if you can explain to them that with actual examples. Don't derive this formula. I'll just show you now. Suppose I start by saying an object is moving at 3 meters per second and has an acceleration of 2 meters per second square. Now what is the meaning of 2 meters per second square? Every second you will increase by 2 meters per second. So that means 1 second later, what is going to be your velocity? 3 plus 2, 5. 1 more second later, 3 plus 2 plus 2. So that's going to become 7, right? And 1 more second later, 9. 1 more second later, 11. Okay, suppose I continue like this, 40 seconds later, now we can't sit and add. So what do you do then? There will be enough kids who will answer that question. So 3 plus 2 plus 2 plus 2, 40 times. So you say, okay, it's going to be 3 plus 40 times 2 or 2 times 40. Then you ask, okay, what happens after t seconds? 3 plus 2t. So that means why the 2t came in there? Because you are adding 2 t times. Well, what if it was 0.3 times? Well, then you say that that's an extension, because once you get it for natural numbers, then you can extend it for others. Okay, so the idea then is that once they get this far, then you say, okay, wait a minute, what if this was not 3, what if this was 5? 5 plus 2, 5 plus 2 plus 2, 5 plus 2 plus and so on, and so you will get 5 plus 2t. Okay, what if this was not 5, but it was 7? 7 plus 2t. What if this was u? U plus 2t, okay? And what if this instead of 2, you are adding 3 every second, u plus 3t. And then finally you say, okay, what if I was adding a every second? U plus a, u plus a plus a, u plus a plus a plus a, and so u plus t times a, or u plus at. Now, is all this really required? Actually, it turns out that yes, it is. They can substitute into the formula, but once they learn it like this with a sequence, then what happens is that the whole process is in their minds, not just the final formula, because ultimately, I would say, at least for myself, and I'm pretty sure about all of us too, and definitely for students, that when you look through a derivation, you look at the final answer. Yes, you do know the derivation, but if you don't understand the final answer apart from the derivation, then you've not understood it at all. Many times the derivation is very boring, too long, very careful steps. Over time, mathematicians have become very careful because there are dangers to becoming overexcited about a particular direction in mathematics, like limits, for example. Then what happens is mathematicians put a lot of extra stuff to make it precise. But then, when you're just learning the basics of many of these things, the fun part is gone because you're too precise. By the time you get to the preciseness part, you are accurate, but you don't understand what you're talking about. Between the two, I will always say, it is better to know what you're talking about than to be accurate. Because if you're accurately not knowing what you're talking about, versus you are not accurate, but you know what you're talking about, I would always go for the second. Okay, let us take another example. So I think it's good to make some things concrete. Let us take the example of limits. Now, let us ask one simple question. Why is this whole process of limits even there? How come when we talk about 7 by 2, I never get a problem? 5 by 5, I never get a problem. Why is this 0 by 0 alone creating mess? No, that's creating a mess, right? Why does it create a mess? Why is 0 by 0 indeterminate? How many zeros are there in the 0 means? Correct. Correct. And then why does this limit even work? How does this whole process of limits work? What is limits? So you are saying 0 by 0 we cannot find, then suddenly we put some LIM before in front of it, then we can find? No, because if children don't get the sense of why 0 by 0 is something special, then the whole process of rest of calculus becomes very messy. The rest of calculus is some formal procedure. Okay, so let us try to see if we can give some reasoning behind 0 by 0. Let me ask some questions first. Suppose I say, let us first understand that while we like to have precise mathematics, all mathematics at some level is an approximation. I mean, while we'll try to make it precise, any practical way of thinking about it, like let's take geometry. Let's take a dot. Let's take a point. Point has no dimension. But if I draw it, there are at least a trillion, million, billion atoms that can fit inside that point. You can never draw a dot which has one atom. Nobody can see it. You draw a line, line has 0 thickness. But if you draw a line, actually it will have a lot of thickness, not 0. And if I draw with a chalk piece, the line is quite thick. Okay, so if I take a number line and I say 0, what do you mean by 0? That point is 0. Okay, fine. This point is 1, that point is 2, 3, 4. Minus 1, minus 2, minus 3. Let us say, show me 2. Suppose I ask you to show me 2, what will you do? You will show this. Now look at the thickness of the finger. If I go and touch this 2, and let's say the child's finger was even smaller, or even you used a pen and did it, actually you are talking about a whole range. Anytime you touch 2, you are actually talking about a range of numbers that you can call 2. Right? So we are talking about a number that is approximately 2. All of these numbers are approximately 2. What kind of numbers are these? 2 point, maybe I'm quite terrible with my finger, so maybe it was 2.1. So 2.1 I'm calling 2. 2.03 I'm calling 2. 1.97 I'm calling 2. Okay, all these are 2's. So when we say 2 is, let's pick 2, actually you're not picking 2 at all from the number line, you're picking from a basket of 2's. Think of it that way. When I pick a 2, it could be 1.97. It's not a very good 2, but it's still a 2. Okay, it is no longer the 2, it is a 2. Right, there are many 2's. Now, this is a very, very good 2. This is also a very, very good 2. In fact, maybe even better 2. Okay, so there are levels to which numbers are closer and closer to 2. Okay. Now, I could do the same with minus 1. I could do the same with minus 3. So minus 3, pick a number and tell me it's close to minus 3. Just come up with some number. Minus 2.999 something. Right, very good. So obviously, you can pick a whole bunch of numbers around this. You can pick a whole bunch of numbers around 4. Now let us say I pick a number, when we say 4 by 2, what I mean is pick some number close to 4 and some number close to 2. So pick a number close to 4. 3.9997, okay. and pick a number close to 2. Let us say 1 point. Why should we make this also less? Maybe make it more. 2.0001. Okay. Now, what do you think will be this ratio? Almost 2. It will be one of those numbers that we would like to call 2. Is that okay? Yeah. Now, let us do the same with 0. And before we get there, what I want to do is to ask you to do some approximations. Can you all just, I'll give you a bunch of numbers here. I would like you to tell me what you think is the approximate value of this number. Okay, so let us start. 197.325. I would like you to write it in your notebook. First one. Second one. 34.007. 100.009. Okay, and let us say 0.001035 and 0.0000000002. And let's say the sixth number is population of India. Seventh number, population of Chennai. Okay, so can you just write down answers to each of these? Actually, I'll give you one more, 8. Let us say it is 1.3 billion plus 30 million. Okay? So, how many have finished this? Just quick approximations. Whatever you think is a good approximation to that number. Done? Okay. So, what was this approximation for first one? 197. Okay. And what did you approximate for 2? 34. What did you approximate for 3? 100. And what did you approximate for 4? 0. So, you approximated this to be, let us say 0. Okay. And what did we approximate fifth one? 0. What about the sixth one? 1 million. Billion. Okay, 1 billion. Anybody had a different approximation? 1.2 billion. Okay. A billion is 10 power 9. So, I will write it as 10 power 9 or 1.2 into 10 power 9. Okay. Population of Chennai? Some number. About 10 lakhs. Okay. It's more like 70 lakhs actually. So, let us say it is 70 lakhs. Okay. And what about the eighth one? 1.3 billion. Okay. Let us think about, where do you think you made the biggest errors? No, wherever you think you have made approximations, right? So whenever you make an approximation, you miss out bunch of numbers, right? You lose out something. Where have you made the biggest errors? Last one or this one? What do you think? This one? How much error did we make there? 30 million. Okay. And when we're making a population of Chennai 70 lakhs, are we sure that we didn't just kill a couple of lakhs? Maybe. And when you say population of India is 1.2 billion, probably we just missed out. Not some millions, more like 100 million, 200 million people we just killed. Okay, we have killed more than the Chennai population. Okay, so we have to remember that we are okay with this saying, there are so many people in India, plus or minus 100 million, like Chennai or Nalanji city pona paravailla, abdin solrom, effectively. Actually, you did not make big errors there. The biggest errors were here. Let's try and understand that, because if that is not clear, the whole of calculus is gone. Let's think a little about it. What is an approximation? Approximation is you keep something and you throw something out. So there is this story that if Bill Gates drops a $100 note, this guy is so rich that doesn't have to bend down and pick it up. You have to, he wastes so much time picking it up. Okay, now Bill Gates can say that. How many of us will feel $100 is about 6,000 rupees? If you drop 6,000 rupees, let me just walk away. How many of us will say that? No, right? For us, that $100 or 6,000 whatever rupees makes a big difference. For him, it may not. I'm quite sure he will also probably bend. I don't know, but okay. But the basic idea is that if somebody says 10,000 rupees, pona pordu paravalla. Now that person must have, hopefully, a lot more than 10,000 rupees. If this guy earns 2,000 rupees, 3,000 rupees, I work with many families which earn a total of only about 2,000-3,000 rupees as a family. For them, 10,000 rupees is huge. That is many months' income. Okay, for somebody to say 1 lakh rupees paravalla, they must be having several crores, right? So, what you neglect depends on what you have. Hopefully, what you have is lot more than what you neglected. So, when you say 100 million population plus or minus, you're not Cuba. Okay, you are definitely not Nepal, or you're not a very small country, Singapore, because Singapore's population is less than 100 million. So, India can afford to say plus or minus 100 million. So, when you say 1.2 billion, actually you are saying I'm not counting several million, because what I have is so large that this is a good approximation. When we say 70 lakhs is the population, plus or minus 2 lakhs. 2 lakhs has become small because the actual amount that you are keeping is 70 lakhs. 1.3 billion you retain, 30 million small. 197 you keep 0.325. In fact, if I had said that this was 190, it's still a good approximation. Because what did I throw out? 7. 7.3. 7 itself I have thrown out. So compared to 197 small, not too bad a problem, right? Compared to 34, that is very small. But if you take this one, what did you throw out? 0.001. What did you keep? 0. Which is the one that was bigger? It is like you are saying, Bill Gates said 1 million, thuki pottala. So I also said 1 million, thuki pottala. Bill Gates can say it, but you can't say that, no. So, I mean, given teachers don't necessarily earn like software engineers, so we'll then assume that this statement is generally true. Okay, but if you take this, what you are retaining is really, really small compared to what you are throwing away. In fact, what you retained is infinitely small. What you threw away was not 10 times, not 50 times, not 100 times, not billion times, was infinite times what you kept. And that's a problem. Why is it a problem? Because even this, if you say this is approximately 0, we have made an infinite error. Infinite error. Please remember that. In fact, for 0, every approximation is a bad approximation. In fact, that's the only number for which no approximation works. Because whatever you throw is bigger than what you have. What do you have? 0. So what you threw is infinite times what you have. And so the problem with 0 is, if I approximate 0, like we approximate everything else, if we approximate 0, let's take one of the 0 approximations. Maybe the first 0 approximation that you thought was approximate is this. And the second 0 approximation was that. We called this 0, we called that 0. Now the problem is, this ratio is a very large number. But it could have been that this was the numerator and that was the denominator, in which case the ratio becomes a very small number, which we might like to call 0, and still we made a big mistake. So the whole problem with 0 is that 0 cannot be approximated. And the whole point with limits is all numbers are approximate. So when you pick a number, you are saying, let's pick a number around whatever we call 2. That is the whole idea of limits. And the reason 0 becomes a problem is whenever you say around 0, the number you are picking is hugely larger than 0 itself. Whereas when I say let's pick a number around 4, you can pick a decent number around 4, which is close enough to 4, in the sense that the error you have made in picking that number or calling it 4, the error is small compared to 4. But when I say 0.0000001, I'm calling it 0, the error I have made is very large. So that is the only number which starts to create this type of problem. So then how do we deal? So that's where the whole idea of limits comes. So then, for example, when I introduce limits in a class, what I would do is, once they understand that this is the problem, then you see that actually the problem is that when I'm making this approximation and I'm calling it 0, usually I just randomly make the approximation without worrying about how good the approximation is. You don't care whether it was 3.997 or 3.999999997 or even 3.9. If it was 3.92, I don't care. We don't care because they are all good approximations. But with 0, every approximation is a bad approximation. So then what happens? So if I want to take the ratio, it is not good enough to say, make the approximation, then take the ratio. First you have to take the ratio, then make the approximation. That's the basic idea of limits. So in fact, the way I would introduce is, there are many zeros. There is 0, 1, 0, 2, 0, 3, 0, 10, 0 billion. So 0 is a set of numbers that you might like to call, maybe you want to call 10 power minus 20 a 0. It is one of the zeros. It is a 0. 10 power minus 100 is a 0. It's a real, much zeroness is a lot more than 10 power minus 20. Then you can also have 2 into 10 power minus 100. You can have 10 power minus 10, which is not a very good 0, but it's there. Maybe you can want to call it a 0. Now all these are zeros. Now when I want to do 0 by 0, you are not actually saying 0 by 0. You are actually saying pick one from here. Maybe you pick 10 power minus 100. Maybe he picked 10 power minus 20. What do we get? 10 power minus 80. Will you call that a 0? Yeah, if you call 10 power minus 20 itself a 0, then 10 power minus 80 definitely is a 0. So this could be a 0. But if it was in reverse, 10 power minus 20 by 10 power minus 100, you get 10 power 80. What should you call this? It is the opposite of a 0, right? What should we call that? We'll call it infinity. So infinity is another set of very large numbers. Now, mathematically, these are not precise. But unless you get a feel for it, I feel that it becomes difficult when people are getting introduced to it to directly jump to a abstract way of thinking about it, because they are used to a more concrete way of doing it. So this becomes 10 power 80. We will call this one of the set of infinities. I'm not saying 10 power 80 is infinity. It is one of those numbers. It's a very large number. By the way, this itself was not correct, that was not correct, this is also not correct. So in mathematics, we have become very bogged down by being super correct. We should learn to become a little bit more free, because then mathematics gives a lot of scope to play around. Okay, it's good fun that way. But you can also say that the first number I selected was this, and the second number I selected was that. In which case, it gives me 1 by 2. But the problem is, I don't know which of these were that 0 and this 0. So here is where the reality comes in. But in all real problems, you will know that 0 and this 0, the relative sizes. Maybe, for example, you are trying to, when are you going to do limits? For example, when you want to find speed or velocity. When do you find speed? What do you do? Displacement, time. You are going to take the ratio. But if you look at displacement and time, generally you will find that displacement time, there is a relationship. It is not pick any 0 or pick any 0. It is pick, maybe the displacement was a function of time. It was 2t square. Okay. And time, of course, is t. Or maybe it was 3t plus 2t square was my formula for the displacement, let us say. Then, if I look at this, yes, it becomes 0, but it doesn't just randomly become 0, because it is related to this 0. When you see these two together, then you realize, oh, okay, that this actually behaves like 3 plus 2t, and as the time becomes smaller, the idea is that time is now 0. But it is not, it was never, even earlier it was never a absolute 0, it was a relative 0. In fact, if I put in numbers like t is 10 power minus 20, what would this be? 3 into 10 power minus 20 plus 2 times 10 power minus 20 square. Now the whole point for them to realize that compared to this 0, that 0 is really, really small. So compared to t square is very, very small. Now these are all about approximations, but that's something that they can calculate. For example, if I actually in class, what I would do is to make them write down. Take 0.0001, square it, write it. Because once you write the number of zeros for 0.001 square, then you realize, my God, so many decimal places away. And if I add 10 power minus 20 square, writing it as 10 power minus 40 never gives a full sense. Because when you finish writing 10 power minus 20, it will finish off somewhere there. But when you have to write a 10 power minus 40, it will keep going. So what happens is, you realize that there are so many extra decimal places that we can actually ignore it compared to this. So once they get the sense of approximation, get a sense of what 0 by 0 is in that sense, then a lot of calculus also starts to become more useful. Like, so when you say sine theta is approximately theta, we introduce that as an idea, they should be able to do certain calculations and realize that there are mistakes with it. For example, if you say sine x is approximately x, what should the limit of sine 5x by sine 7x be? Well, sine 5x is approximately 5x. 7x, sine 7x is approximately 7x. So answer should be 5 by 7. Now is this correct or wrong? Why is it wrong? Why is this particular thing wrong? Actually, it turns out this is not wrong. Okay, what would be wrong is, there are dangers involved here. For example, if I wrote x minus sine x by x cube, and I said, oh, sine x is approximately x, x minus x by x cube, 0 by x cube, 0. Now that's wrong. But this is still correct. Now the question is, why is that wrong? Why is this correct? Here also I made an approximation, here also I made an approximation. So let's go back to the original idea of when is an approximation good. The real problem is only the approximation with 0. Whenever what you keep is much larger than what you discard, what you throw away, then the approximation is good. Okay. Now, if I say 1 plus x is approximately 1, x is small, let's say x is close to, we're going to say x goes to 0. If I call this, is this correct? Yes. What about 1 plus x minus 1? If I call this 0, now it is wrong. Why is this wrong? If that is correct, shouldn't this be right? Because the 1 got killed. There is no 1. What I threw out was very small compared to what I kept. Unfortunately, now what I have kept is 0. So what I threw out was x, which is very large compared to what I have kept. So approximations don't work the same way as regular subtraction, as exact. So one way is to say just always deal with exact. Another way is to just play around a little bit with this, get a feel for approximations, and remember that there are dangers. Yes, there is this danger. Here, it is not really sin x is exactly x. Sin x is x plus some things. Now, those some things are much smaller than x. So when x goes away, those things become important. Like many of you are aware about the evolution history maybe. So there was an age we call the Jurassic Age. What is that? What lived in the Jurassic Age? Dinosaurs. Now, what about our great ancestors? Were they also alive at the dinosaur age? Otherwise, you won't be alive now. Life did not start after the dinosaur age. So, age of dinosaurs is actually dinosaurs plus rats, because our great ancestors were like rats. Actually, nobody likes to think of it. We all like to think we came from monkeys. Problem is, where did monkeys come from? Monkeys came from rats. Okay, now we don't like that very much, but okay, but where did the rats come from? Okay, so maybe Palli. Right now, let's come back to this age of dinosaurs, very simplified version of it. Age of dinosaurs is dinosaurs plus rats, approximately dinosaurs. Right? Now the problem is, if you said Jurassic is dinosaurs plus rats, and there are many other things also, and we called it approximately dinosaurs. When an asteroid comes and destroys the dinosaurs, and you just say, oh, dinosaurs all dead, everything is gone, then at the end of the Jurassic, we will not be alive. Nothing is there. But when the dinosaurs get killed, it becomes the age of rats. Today is the age of rats, I mean, literally. Because all of us have evolved from those rats. All mammals, deer, tiger, lion, everything comes out of that. So when you subtract the dinosaurs, this does matter. Right? That is exactly the whole purpose of a lot of stuff in limits, how to make this careful. So how do you make this fact careful? But if they don't use this at all, they are not using limits. For example, if I had given a question that looks like this, what do you think the answer should be? 6x plus 5x plus something very small compared to 5x. But this is big 6x. So if it is small compared to x, it's small compared to 6x. So ignore. So when you ignore, what do you get? 6x, 7x, therefore 6 by 7, and that's correct. They should know that that is correct, and it has its dangers. The only danger they have to keep in mind is that if you subtract off that x, then whatever was left out, the rats start to matter. Okay. Now, that doesn't mean you don't play with this. You do play with this. And what if I had 2 of this minus x, 3x square? What will you do? Well, compared to x, x square is very small. Let's understand whether x goes away. It doesn't, because this is 5x, 2x, 7x, 7x by 7, 7x, so 1. Okay. What if I had let us say, minus, it still doesn't go away because it's 2x minus 5x. It should not become 0. That's the only condition, right? So minus 3 by 7. Okay. And if I had plus, what do we do? Well, this is minus 3 by plus 3, so minus 1. There are dangers with it, but the problem is danger should not mean we don't go out and try out a little bit. It is like saying when you people go on the road, there is a danger that something can come and hit us. So we'll stay at home. Then the whole fun of going out itself is lost. So the whole fun of mathematics lies in knowing the danger. Because once they realize, oh, this is the danger, then the formal way to actually avoid the danger is to use epsilon, delta, to use those more formal ways of calculating. For example, we might teach that you must not do the limits 2 times, for example. You can't just substitute and then figure out. You can't do the approximation. It is correct. You should not do it, but we should know when we can. Because otherwise the purpose of what that mathematics means itself is then lost. So many times what we found is that we create many more steps. Sometimes we'll also have to understand what that really means. But if we create many more steps, it makes a lot more sense. Like, I'll give you one example alone now, and I think it's time also. Okay, so I'll just give one example of what we try to do. The thing here is, we have learnt a lot of GP. For example, is series, kids learn a lot of stuff in series. It is actually an amazing fact. I mean, the problem sometimes is that we learn today many, many facts, and we don't have time to appreciate those facts. There was, in Greek times, it was a great puzzle that you can add an infinite number of things and still end up being finite. It was called Zeno's paradox. Okay, so the paradox starts off with something very interesting. So it says, if there was a tortoise, so let us say that there is a tortoise here. And there is this very fast runner. I think his name was Achilles. Okay. Now, you know that if the tortoise is, let us say, 10 meters ahead of Achilles, of this guy, will Achilles be able to catch up with the tortoise or not? Should be able to catch up, obviously, right? I mean, if there is somebody very slow, there is an ant going there, I don't expect that I will take forever to cross the ant. But this guy came up with a very nice idea. So his question was, let's not jump to conclusions that this guy is going to cross. So let us say this guy's speed is 10 meters per second. Tortoise is moving at 1 meter per second. I mean, that's too fast for the tortoise, but let's just assume. So this guy's argument is, right now tortoise is ahead. How much time will this guy take to reach there? 1 second. So by the time this guy reaches there, tortoise chumma it will have moved, right? It would have moved a little bit. Now, this guy is going to take time to get from here to there. How much time? This guy took 1 second. Now he's going to take 0.1 seconds. But in that 0.1 second, tortoise won't be there. So it will move a little bit. Then this guy will take 0.01 seconds to reach there. In that time, the tortoise would have moved a little bit. So he'll never be able to reach the tortoise. Correct? No? Argument sounds correct. What's the problem with the argument? So by the time I reach here, you are a little bit ahead. By the time I reach there, you are a little bit ahead. By the time I reach there, you are a little bit ahead. You are always ahead. So when did I cross you? So what is the problem here? The problem is, the total time is 1.11111111 seconds. Now, it has an infinite number of steps, infinite number of decimal places, but it's actually less than 2. It is less than 1.2. So you can add up an infinite number of things and still end up with finite value. Okay, now this is not an obvious statement. Zeno was a reasonably smart fellow and had great difficulty with infinite steps adding up to finite time. So the idea here is, can I take a finite amount of time or length and cut it up into infinite pieces? Actually, yes. So for example, we teach them about GP. I usually find it a lot of fun to talk about this. What is the sum of all this? And they have to get to understand that actually if you break it up into infinite number of pieces, it is easier to add than finite number of pieces. Adding 20 of these is a mess. I never like to add 20 of these. But adding an infinite number is easy. Why is that easy? So let us say that there was a piece of paper. Let's call this 1. What is half? Half plus half, 1. Let's cut this into half. What was this? 1 by 4. Half 1 by 4, 1 by 4 is 1. Right? Cut this into half. 1 by 8. Half plus 1 by 4 plus 1 by 8 plus 1 by 8, 1. Cut this again, 1 by 16. Cut again, 1 by 32. The leftover is becoming really tiny, but you can still cut it into half. If I keep on doing it after a long time, there is no leftover, or the leftover is really tiny. So what does this whole thing add up to? 1. So therefore, half plus 1 by 4 plus 1 by 8 plus 1 by 16 is 1. Now, we can also derive it by saying S is equal to 1 plus x square plus xs is equal to x plus x square plus x cube, and subtract and cancel that off, and you can say 1 minus x times s is 1. Now what has happened here is, there is a formalism here, there is formal way of proving something, but at the end of it, people don't believe the answer. At some level, mathematics or sciences, we need to believe. Too much of formal jargon there takes us away from belief. அதெல்லாம் கரெக்ட், ஆனா நிஜத்துல ஒர்க் ஆகாது. இல்ல நிஜத்துல ஒர்க் ஆகும். Because if you realize that நிஜத்துல ஒர்க் ஆகும், that this really is one, then suddenly this formula becomes a lot more intuitive. People start to say, oh, okay, this is something I can figure out, I can derive. If it's only a formal trick, then there is a loss of belief. And I think one of the things that's happening in many times in mathematics in higher school is they don't believe it anymore. They know to do it sometimes. Some kids don't say, I don't believe it, I can't do it. I believe the earlier one, I can do it. But now I can't believe it anymore. So this is nonsense, this is not correct. You know, something they have written, some proof. But at the end of it, it is not something I trust. So there is a factor of, I mean, you may say mathematics, belief, feeling, trust. Why are these words there in mathematics? But they are there because we are human beings and they are there in us. So in mathematics particularly, I feel it is very important to not just derive something like this and show, therefore substitute x equals half. That's okay. That's one way to go about it. But doing it like this and showing is equally important. In fact, now somebody can come back and say, okay, idukala manna, what about 1 by 3? What about 1 by 4? So how will you do this for 1 by 3? 1 by 3 plus 1 by 9 plus. How do I do this? So here is one proof for it, or one approach. Cut it into 3 parts. 1 by 3, 1 by 3. Instead of cutting that, I'm going to take the middle one and cut it into 3 parts. What is this? 1 by 9 1 by 9, 1 by 9. So this is 1 by 3, 1 by 3, 1 by 3, 1 by 3 is 1. Cut it into 3 parts, 1 by 27. And if you keep on doing that, the middle piece is going to become very, very small. In fact, this idea that the middle piece becomes very small is the whole idea when we say limit x goes to 0 or n goes to infinity. What is the meaning of that? Visually, you should be able to see that it's actually becoming very, very small. So once we see that, you can say that this whole sum is equal to this whole sum, but this plus that is 1. So what is this? Half. What do you think will happen if I have 1 by 4 plus 1 by 4 square plus 1 by 4 cube? Now kids should be able to derive geometric ways of thinking about it. Take that piece, cut it into 4 parts. Take one of them. Now it's very hard to take the middle piece. Take the fourth piece, cut that into 4 parts and add it here. You will be left with one piece. Add the next one. So if they start to figure this out, suddenly it has become real. So the whole point I feel in mathematics is to create many of these steps. So we can assume that in the step vana. But if you don't have the steps, you are asking people to jump from there here straight away. Some kids will. Maybe they go outside, learn some steps and come. But it is not surprising that most children say, I cannot jump this much. I don't like this game anymore. These were children who liked the game earlier. So if we can break it up into smaller steps, make it more and more concrete. I know that there is a problem, pressure of syllabus, all of that is there. So when do we have time to do this? But even if we do a little bit of this and kids see that there is some reality to it, what it does is for them to search out a little bit more. It increases their attention span, increases the focus. In fact, one of the things we are now doing is to do a lot of this type of research on where do kids find it difficult. And actually, it's quite fascinating to find that out and look at what confuses them. Every time there is a chance to find out what confuses them, I find it's very, very clarifying for me. Okay, so I know it's time, so I'll just end with one example of what it did when I started off doing this research in the beginning. So I was going and teaching algebra and I thought I was a good teacher until I had this experience. So this is the girl, I was trying to help her out. She was in the 8th standard and struggling a little bit, in fact very close here, Taramanila. And so she was struggling with basics of algebra. So I was telling her that, see, 2 irukku, 3 irukku, 5, 10, 9, these are all various numbers. Now imagine I don't know which number. Why can't I just name it as x? So you are naming x as an unknown number. So whenever you don't know it, it is called x. If you know it, of course, you will call it 9. So suppose I don't know it, and I want to do x plus 1, and I'm telling you now that x is 7. What will you do? Now that you know it, you can say 7 plus 1, so therefore 8. So after a little while, we kept doing this. So I said, okay, 7 plus 1, 7 minus 3. So if I tell you x is 7, then you can do 7 minus x minus 3. So I thought she had got a general hang. I gave her a lot of different types of numbers for x, and she was able to calculate. We even did multiplication. So I said 2 times x. X is 3. So 2 into 3, then it becomes 6. If you don't know, you can't calculate, but if you know, you can then substitute the value. So then I asked her, Seri, idella okay. So what is x plus x? So what do you think she said? Why? So her answer was, so basically her answer was x is an unknown number. Unknown plus unknown தெரிஞ்சா என்ன வரும் சார்? Unknown என்ன நினைச்சா unknown தானே வரும். இப்போ நீங்க தானே சொன்னீங்க unknown னா x. Okay, but is there a problem with the logic? Actually, it's correct. Because x is not just an unknown number, it is a specific unknown number. But I didn't realize that x is a specific unknown number. Because once we've learnt it, we don't know how we do it. How many of us can walk? I'm assuming pretty much everybody, right? Now, we don't know how we walk. We only know that we can walk. You know how to walk, but if people are trying to spend huge amount of effort trying to find out exactly how we walk, just the process of taking a step and doing this, which we can do without thinking, is a very complex idea. So once you have learned algebra, you know exactly what to do, we forget why it was difficult. Once you know, okay, limit na ipdi dhaan pannom, we know it now. For a child who's just getting, yeah, ipdi dhaan pannom. Infinite numbers add pannite, how can you add so many numbers? No, once you know it, you know what to do. But we were not there, I mean, we were there not too far away, except that once we've crossed the boundary, we forget. And in mathematics, there is a lot that we need to learn as we work with children. And basically, that is one of the things that I found. That every time you ask, you realize that problem is not that avanukku puriyala, avangalukku puriyala illa. Enakku puriyala. Because we have to first figure out that there is a gap in what we are saying. I only know that I can be here. I don't know how I climbed up. I don't know there are 4 steps in between. I don't even know those 4 steps. And that is partly the problem with many times teaching mathematics. Because teaching mathematics, the biggest problem is for us to learn mathematics. Because we don't know many of the things that are there as gaps. And as we teach, as they ask doubts, we go look up, come back, and you realize, oh my God, there is so much more that can be done. So one of the things that we are doing now is, as a team, we spend time to understand children's problems and come back and rethink about whether we are doing it the right way and whether we have understood the right way. And many times, actually, we have not understood the right way. So we'll have to go back and rethink what needs to be done. And we are also trying to use technology, because today's generation is fully technology driven. They can use cell phones much better than we can use. So idea was, can we use that to increase moments for like lot of attention span? Can we increase that? For example, can we throw a puzzle that when they solve, immediately they are able to share, they are able to discuss. And as we increase that, I feel that technology can actually become, instead of a distraction, it can become something that can help learning process. So yeah, thank you for once again for the opportunity. Questions? So my answer to that would be that as you are getting closer and closer, like in this case, that process of becoming closer and closer is limit. So what happens as x becomes closer and closer to 0? What happens as I make the number of parts larger and larger? So that we will call it as number of parts becoming closer and closer to infinity. I mean, that doesn't mean much, because closer to infinity doesn't mean this close. Closer to infinity means larger than everything we know. Okay, but the idea of limit is that it is not yet complete. You are getting there. I have never got infinite steps, but I'm getting there. So as I get there, what happens? Because in the real world, everything is about approximations. So for example, a lot of calculus would not have been possible even by the Greeks, for example, when they were doing mathematics, because they were always looking at pure mathematics with exact values. In fact, they got very confused once they had infinities, then immediately they started getting thoroughly unhappy with the number system. But physics requires calculus. It's almost like an essential thing. That's one of the reasons why Newton discovered a lot of stuff in calculus, because you need it where there's no other option. Because in the real world, it's always time, for example, is never going to be 0. You will always have a small time interval. But it is important to know what is instantaneous velocity, right? So in that case, what are you trying to calculate? You are trying to say, well, if I travel for 2 seconds, how much would I have gone? Instead of saying 2 hours, let's take 2 seconds. But a better number would be to take 0.2 seconds. Even better would be to take 0.00001 second. Even better would be to take 10 power minus 20. But if the calculation gets very, very hard as I do it, then obviously it's not very interesting or useful. Turns out that as I make the number smaller and smaller, as I make the time smaller and smaller, the ratio, you can figure out what will happen when you make it smaller and smaller, it gets to a nice value. And that value is what we call limit. Right? So I mean, that is, yeah, you are getting closer to some value. Yeah, you can use that as an example. Yeah, but I think that one example won't be enough. This is a reasonably complex idea that we must use many examples.
So, regarding the complex numbers, the students are asking where are we going to use these complex numbers and how it is going to be helpful to us, to them actually. So they don't have a clear idea about why this is not considered in terms of the real numbers and what is that
So
relation.
my answer typically, so there are two problems when complex numbers. Okay, one problem is generally that people are very unhappy with this root of -1. Okay, I doesn't make much sense. So for example, when I was a student learning this, my problem was if root of -1 is I, root of -2 j nu kupduva, root of -3 k nu kupduva. Chumma extra, but you just keep on, because saying root of -1 is I doesn't seem to make much sense. So there is this unhappiness with complex numbers, which by the way is not true with just children. For almost some 400-500 years, mathematicians had difficulty with complex numbers. Okay, they had introduced this idea, but were not very happy with the idea. It took a long time if you look at history of mathematics. The one way in which I try to address this is to say, real number real illa. Okay, show me 3. Show me 3. Where is 3 in the world? You don't have 3. 3, this is 3 fingers. Symbol, that is just a symbol. So this and let us say this set have something in common. There is no 3 outside. If I close this finger and say, okay, one person out, close that finger and one person out, close this and one person out, no fingers, no people. So there is something common about the 2 which we call 3. We have abstracted 3 out. So that is one level of abstraction which was already unreal. Just to fool ourselves, we call it natural. Okay. Then there was a time when, which we may not remember this natural part, but there was definitely a time where we said 5 minus 2, 3, 2 minus 5 panna mudiyadu. Right? Not possible, because children do answer that. Then suddenly one fine day we said 2 minus 5 minus 3. Now that is unreal. Okay, but then we introduced that as an idea. Then there was a question at some point where if somebody asks you what is 9 by 3, what will you say? 3. What is 8 by 2? 4. What is 7 by 2? Actually was not possible, or 2 by 3 was considered not possible. Now, suppose I ask you what is 16 by 4, is that a question or an answer? 16 by 4, is it a question or an answer? Question. Sure? What's the answer? 4. What is 2 divided by 3? 2 by 3, but 2 by 3, is it a question or an answer? If 16 by 4 was a question, 2 by 3 is a question, how did it become the answer? Now somebody will say, no, 0.666, but that's an approximation. The best way to write 2 by 3 is to say 2 by 3. 2 by 3 was a question to which mathematicians didn't have an answer. And mathematics at every point has grown by saying, oh, here is a question for which there is no answer. Question is the answer. Now you may not like it, but that's exactly true, right? 2 by 3 was a question which became an answer. What is root of 9? 3. What is root of, no, root of 9 is not plus or minus 3, it's just 3. Because that's the way it's defined. It could be, but let us say that it was just 3. Root of 16? 4. Root of 2? Root 2. Is that a question or an answer? Question. We didn't have an answer in any other form, and we say that that particular field or set in which we were doing things we couldn't find we can ask the question in that set, but we cannot find an answer in that set. And therefore, we come up with a new, the question becomes the way to talk about the answer. So root 2 became the answer. Then for many years, we continued saying root of minus not possible, minus 1 not possible. So now, exactly what we did earlier, if you are comfortable with root 2, how did you get comfortable with root 2? That was a question. So you say, if you got comfortable by saying root 8, you can write it as 2 root 2. It's not very great, but still, you can do something with root 2. And it is because also 1.414 whole square is a mess. But root 2 whole square is a nice and simple thing, we can call it 2. The same way, the point is not that root of minus 1 is I. The point is, root of minus 1 is the question which has now become the answer. And mathematics, the point there is not to try and understand root of minus 1, but is to actually say, can I use it? If I can use this, then it becomes useful. By the way, there is nothing real about natural numbers or real numbers, and nothing imaginary about imaginary numbers. So because the real number line is filled. So, in fact, once you ask that question, I do have no more space here, but there is so much space on the board, and we are only using one line. So why not use those points? In fact, I recently just did a class where I started off with the plane. It's such a shame that we draw one line and use only these things. It's been quite useful to put points on a line, but there is so much extra space. So how about numbering those, which we have, no? We have come up with ideas like x comma y. And then we need to basically make that x comma y, we don't do an x plus y, because then that takes away the distinction between the ordered pair. So now we have an x plus iy. And the great advantage of this is that it can be divided. Okay. Vectors could have also been useful, but vectors you can't divide. Okay. So, like for example, when I was doing this, we started off with unit complex numbers, like unit vectors. You can introduce a lot of that and get them to get a sense of it. So basically, the idea is for them to start seeing that this is not something new. This is an extension of the process they've already got used to. And every time they did that, fractions was useful. Calling 2 by 3 as the answer was useful. Calling root 2 the answer was useful. And so they have to trust that calling root of minus 1 is the answer is useful. And then you do a few things to prove it is useful.